Okay, I think I left my grade book upstairs. So everything on the sheet, so the rest of your classmates. And for those of you out there in Zoom, don't worry if you have signed on now, I will have a record of it, so I'll make sure that I'll consult that list in recording your attendance to today's class. So let's talk about gases. That's what we'll be discussing today. And pretty much for this particular chapter, we'll be looking at, among other things, different laws that govern, just put it right there on the table here, different laws that govern the behavior of gases, all right? So the first law that we're going to talk about, let me make this full screen here. Let me just skip this here. This is just dealing with the kinetic molecular theory. This is a theory which basically deals with the behavior of gas molecules. It's a model for explaining the behavior of gas molecules, and also you can use it to understand the laws that we're about to get into. So I leave that for you to read up. Of course, by now you should have watched the videos posted for chapter 13 in Canvas. If you have any questions about any of these topics, please feel free to contact me, but I'm just going to skip over these and leave that for you to read upon. Let me talk about pressure before we move on to the laws. Now, pressure is oftentimes in everyday language confused with force, right? People tend to use force and pressure as if they mean the same thing. Well, force basically is different from pressure, even though they're related. Force is basically a push or pull on an object, right? So if you push an object or you pull it, that's a force being applied to the object. Pressure is a force transmitted over a particular area, all right? And as given by this equation here, we can calculate it using this equation. Pressure is equal to force divided by area. So what that means is that if the force is in 1 unit and the metric unit of force is newtons, and the area is in meters squared, then the units of pressure would be newtons per meter squared. And there's a special name given to this collection of units. It's called a Pascal unit, right? So whenever you see Pascal, it's the same thing as newtons per meter squared. But there's some other units of pressure as well. Let me just skip this here. So basically, this table here is a summary of different units of pressure. There's a unit known as the atmosphere unit. And that atmosphere unit is equal to each of these values expressed in different units of pressure. You have the torr unit. So 760 torr is equal to 1 atmosphere. 760 millimeter mercury is equal to 1 atmosphere. So therefore, the torr unit and the millimeter mercury unit are both one and the same. And I described in the videos where this millimeter mercury unit comes from. So I'm going to leave that again for you to review. If you have any questions about that, please feel free to contact me. And then you have some other units. You have centimeters of mercury, you have kilopascals, you have millibar, inches of mercury, which is oftentimes what you see in weather forecasts, all right? If you pull up any weather forecast online, when they mention the barometric pressure, which is the same thing as the atmospheric pressure, you'll see that it's quoted in inches of mercury, all right? And then you have pounds per square inch, which is used very often in engineering, I know for sure. So that's another unit of pressure. For all purposes, we'll be using, for the most part, the pressure expressed in either atmospheres, torrs, millimeters mercury, and kilopascals or pascals. I don't anticipate us using these down here, all right? So those are the different units of pressure that we'll be using in this course. And then let me just skip to the first law. Boyle's law, all right? So Boyle's law is a law which relates the pressure of a gas to the volume. And basically what that law says is that the pressure of a gas is inversely proportional to the volume, or the other way around, it doesn't matter which way it's stated, to the volume of a gas, provided that the temperature is constant and the mass of the gas is fixed. So that's basically what Boyle's law states. And if we were to express it mathematically, we can express it this way. I don't know if you're familiar with this symbol. Whoops. I don't know if you're familiar with this symbol. It means proportional to, right? So this is saying that the volume is proportional to 1 over the pressure, all right? Which is basically the same thing as saying the volume is inversely proportional to the pressure. So what does that mean? That means that as the pressure decreases, the volume increases, or if you look at it from the volume standpoint, as the volume increases, the pressure of the gas decreases, and vice versa, right? And if you think about this, especially from our everyday experiences, we know that this makes sense. If you imagine you have a container where you can reduce the volume easily, and let's say you have a gas trapped in that container, as you can imagine, as you decrease the volume, the pressure exerted by the gas will increase, right? And there's a linear inverse relationship. In other words, if the volume is halved, then the pressure is doubled. If the volume is tripled, then the pressure, if the volume is reduced by a third, then the pressure is tripled, and so on and so forth, right? So this is one way of expressing Boyle's law. Another way of expressing it would be, let me write this down. P is equal to K times 1 over V. This is another way of stating it, where K is a constant, all right? Which means that if you rearrange this, you're going to get PV is equal to K. So what this is telling us is that the pressure times the volume of a gas is constant, provided again that the temperature is fixed and the amount of gas is fixed, right? And actually, coincidentally, later on this afternoon, my General Chemistry 1 class will be actually doing an experiment proving this to be true, all right? So if this is true, that means that we can also express Boyle's law this way. P1V1 is equal to P2V2, right? So in other words, P1 and V1 would be the initial pressure and volume. P2 and V2 would be the final pressure and volume, right? So therefore, the product of pressure and volume, regardless of what those values are, will work out to be a constant value, right? And that's what this equation is saying. And this equation is more useful because the thing about this equation is that if you know, or if you're given 3 of these 4 terms, you can easily rearrange the equation to find out the 4th one, right? So for example, if V2, if you rearrange this to solve for V2, let's say you want to find V2, and you're given P1, V1, and P2, we can therefore say P1, V1 divided by P2 is equal to V2, and then you plug the numbers in, and you get your final answer for the volume, all right? And I think I have an example here where they gave you 8 liters of nitrogen, and the pressure is 500 torr. What must be the pressure to change the volume to 3.00 liters, all right? So, you know, this is one of those word problems where you have to read the question carefully to identify what is what, right? So based on what I can see here, the 800 the 8.00 liters would be V1. The 500 torr would be P1, and then the 3.00 liters would be V2, right? So the question is asking for P2, right? So remember now, P1, V1 is equal to P2, V2. So therefore, P2 is equal to P1, V1 divided by V2. And we put the numbers in. So P1 is equal to 500 torr. And what I'm going to do here is put a decimal point there to make that 3 sig figs. And then the V1 is equal to 8.00 liters divided by V2, which is 3.00 liters. And then from here, we have to do the math, and the liters unit will cancel out. Get my calculator. So 500 times 8 divided by 3. So according to my calculation, this works out to be, when rounded off to 3 sig figs, 1330 and the final units will be torr. All right? And that's basically how Boyle's law works. All right? The only other thing I want to add before I give you the first assignment in this chapter is to say that whenever you're using Boyle's law, right, it does not matter what the units of pressure or volume are, as long as the units of pressure and volume are the same on both sides of the equation, right? So in other words, whatever the units of P1 is, the units of P2 would have to be the same. Whatever the units of V1 is, the units of V2 would have to be the same. All right? So if P1 is in atmospheres, P2 must be in atmospheres, right? And the reason I mentioned that is because you could be given a question where P1 is in atmospheres and P2 is in, let's say, torr, right? So when you're faced with that situation, then you either have to convert the torr units to atmospheres or the atmospheres to torr before you plug the numbers into the equation and then solve for whatever the question is asking for, all right? Okay, any questions about this example? Any questions? Any questions? Okay, so with that said, let me give you now assignment number 13. And by the way, I don't know if I mentioned this, but the last chapter we did was assignment was chapter 10, and now we're in chapter 13. You might be wondering why I skipped 11 and 12. And the reason why is simply because the topic in chapter 13, dealing with gases, as far as I'm concerned, is a natural follow from the topic that we discussed in chapter 10, which was energy. All right, so that's the reason why we're doing chapter 13 right now. Right? So what I want you to do for now is to focus on questions 1 through 6. All those questions under the Boyle's law section, right? Questions 1 through 6. So basically, all those questions will be using, you will be using P1 V1 is equal to P2 V2. All right? So work on that right now. Oh, and by the way, for those of you out there in Zoom, I don't know if I published that assignment online, so let me check and make sure. Okay, so it's now published, so you guys out there in Zoom can work on questions, what did I say? Questions 1 through 6. Oh, and for those of you guys who came in here, I forgot my grade book, so make sure you sign the sheet and pass it around. Okay, everybody in here sign this. All right, thank you. Okay, so are we finished with those questions, 1 through 6? All right, so the next law I want to discuss, let me bring this back up. Oh, I just saw somebody leave a message. Oh, okay, Mr. Farrell, I did not call attendance because I left my grade book. I think it's upstairs in my office, so I will still have a record of your attendance since you have attended online via Zoom. Okay, so let me talk about the next law, which is Charles' law. And this law relates the volume of a gas to the temperature, right? So this is Charles' law expressed in words. At a constant pressure, the volume of a fixed mass of gas is directly proportional to the absolute temperature, which means it's temperature expressed in Kelvin, all right? So basically what this law is saying is the volume is directly proportional to the temperature, but very importantly, the temperature must be in Kelvin, all right? So if you're given the temperature in Celsius, when using this law, you'd have to convert it to Kelvin, right? And to convert it to Kelvin, as you remember from chapter 10, you add 273 to the value expressed in Celsius, right? Another thing I need to mention here is that in this particular case, the pressure and the amount of gas, I'm going to use N to represent the moles of gas, must be fixed or constant, all right? So another way of stating this law is the volume is equal to K times T, where K is a constant. And yet another way of expressing this law is volume over temperature is equal to a constant. So we can also say that V1 over T1 is equal to V2 over T2, all right? So if V1 and T1 are the initial volume and temperature, and V2 and T2 are the final volume and temperature, then that's a relationship that incorporates all those variables. So for example, if you're given a problem where you need to find V2, then we can rearrange this equation to get V1 over T1 times T2, all right? For example. So that's basically Charles' law. Okay. So one additional thing I want to say is that in the case of Boyle's law, remember I said that P1 and P2 must be the same, of the same units, and V1 and V2 must be of the same units. The same is true when it comes to the units for the volume in the case of Charles' law, right? V1 and V2 must be the same units. Again, it doesn't matter what the units are. It could be liters, it could be milliliters, it could be gallons, it doesn't matter, right? But in the case of temperature, the temperature must be expressed in Kelvin, right? So if you're given a problem where you need to use Charles' law, then you have to make sure that all the temperature values that you're going to plug into the equation must be expressed in Kelvin. And in fact, a couple of the problems in your assignments, I think, like the very first one actually, you have to do that, right? They gave you the temperature in Celsius. You have to convert it to Kelvin by adding 273, and then you put it into the equation to solve the problem. Let me see if there's an example. Let me just skip all this here. Okay, so here's an example. So let me work this example for you before you do the problem in the assignment. So this question says a 25 mil sample of nitrogen at 75 degrees Celsius is confined at a pressure of 3.0 atmospheres. If the pressure remains constant, so the pressure does not change, right? What will be the volume of the nitrogen if its temperature is raised to 250 degrees Celsius, right? So in this particular case, again, it's one of those questions where you have to read and figure out what is what. So this here, the 255 mils would be V1, the initial temperature T1, which would be the 75 degrees. We don't need to worry about the pressure because the pressure is constant. But the final temperature here, 250 degrees, is T2, right? What the question is asking for is V2, all right? So basically, this is the law. V1 over T1 is equal to V2 over T2. So we need to find V2, which is equal to V1 over T1 times T2. So before we plug in the values, I'm going to convert the 75 degrees T1 to Kelvin. So 75 plus 273. So this is equal to 348 Kelvin. So that's T1. And then in the case of T2, 250 plus 273, this is going to be equal to 523 Kelvin. All right. So now we can put the numbers in. V1 is 255 mils times T2, which is 523 Kelvin, divided by T1, which is 348 Kelvin. And of course, the Kelvin units will cancel out here and here. And the final answer is going to be in milliliters. So 255 times 523 divided by 348. And according to my calculations, this works out to be equal to 383 mils. And that's how you do that. All right? Any questions? Any questions? No questions? Okay. So based on what I've just done, you should now be able to do the Charles law questions, which starts, and there are only two of them, right? So you should make quick work of that section. All right, so do that one or do those two, and then we'll move on to the next law, which is Gay-Lussac's law. Okay, I'll give you one more minute to finish up on Charles Law questions. Okay, so the next law is Gay-Lussac's law. And this law is kind of similar to Charles' law that we just looked at. Basically, what this law says is that there's a direct linear relationship between the pressure of a gas and the temperature, provided that the number of moles of the gas is fixed and that the temperature, or not the temperature, but the volume is fixed as well, right? Again, as in the case of Charles' law, the temperature must be expressed in Kelvin, all right? So again, if you're given a temperature in Celsius, you need to add 273 to that value to get the equivalent value in Kelvin. So this is one way of stating it. Another way of stating it is in this form, and you can immediately see the similarities between the Gay-Lussac's and the Charles law. The only difference between them is that instead of volume terms, you have pressure terms in the equation, right? So basically, you can use this equation to find the fourth term if you know what the other three terms are, all right? So that's Gay-Lussac's law. And here's an example. Yeah, do this here. It says the temperature, or at a temperature of 40 degrees Celsius, an oxygen container is at a pressure of 2.15 atmospheres. If the temperature of the container is raised to 100 degrees Celsius, what will be the pressure of the oxygen? So again, it's one of those questions where you need to identify the different terms. So in the case of this question, this obviously would be T1. This would be P1. And this would be T2. And the question is asking for P2, right? So since we know that P1 over T1 is equal to P2 over T2, then we can rearrange this to get the expression for P2, which is P1 over T1 times T2, and then we put the numbers in. But again, as I said before, we need to convert these temperature values to Kelvin. So it's 40 plus 273, and that gives you 313 Kelvin for that. That's for T1, and for T2, well, this is easy. This would be 373 Kelvin. And then we put the numbers in. So P1 is 2.15 atmospheres. T2 is 373 Kelvin. And T1 is 313 Kelvin. So let's see what this gives. 2.15 times 373 divided by 313. Okay, so according to my calculations, this works out to be equal to 2.56. And this was Kelvin, which will cancel out with that Kelvin unit. So the final unit here would be atmospheres, 2.56 atmospheres, all right? And that's basically how we do this problem. And let me say here that, again, kind of similar to what we said with respect to Charles' law and the units for volume, V1 and V2, in the case of Gay-Lussac's law, the units of P1 and P2 must be the same, right? Before you can put the numbers into the equation and solve it, all right? So that's basically the Gay-Lussac's law example, which should enable you to do the Gay-Lussac's questions. There are 4 of them, so you can get started on those now, and then we'll move on to other things. All right, let me give you one more minute to work on Gay-Lussac's law problems. Okay, so the next law is a combination of the laws that we have just discussed. Let me put this up. Whoops. Let me do this first. Okay, so the next law is actually literally called the combined gas law, and that's because it combines basically the relationship between the pressure, volume, and temperature of a gas, right? So far, we have learned about Boyle's law, which says that PV is equal to a constant. And this is true if the number of moles and the temperature remains fixed, all right? We also learned that, what was the next one? V over T is constant. And this is true if the pressure and the number of moles is constant. And then the last law we learned, Gay-Lussac's law, P over T is equal to constant. And for this law to be true, the volume and the number of moles will be constant. So basically, in all the laws that we have learned so far, there are two things that need to be held constant, right? This law takes into account where the pressure, volume, and temperature does not remain constant. Only the number of moles is fixed, right? So basically, this law here, the combined gas law, is a combination of these three laws right here, all right? And therefore, you know, if you need to find out the sixth, if you need to find out one of these terms, let's say V2, then basically you need the other five terms and then you rearrange it. So let's say you want to find out what V2 is equal to, then that would be equal to P1 V1 times T2 divided by T1 times P2, all right? So all you have to do is put the numbers in and make sure that you do your computation correctly and all of that. Again, the temperature must be expressed in Kelvin. In fact, for all the laws that you're going to meet, if temperature is involved, the temperature must be expressed in Kelvin, all right? Doesn't matter what the pressure units are, doesn't matter what the volume units are, all right? But the temperature units must be in Kelvin, okay? So I think I may have an example using this. Let me just skip all this here. No, I don't. Let me see if I can dig up one from online. Let me see here. Let me see here. Combined gas law problems. I'm just going to arbitrarily choose one. Okay, let's see here. Okay, let me just copy and paste this one into Word. Okay, so here's a question. 500 liters of a gas in a flexible wall container are prepared at 700.0 millimeters mercury and 200 degrees Celsius. The gas is placed in a tank under high pressure. When the tank cools to 20 degrees Celsius, the pressure of the gas is 30.0 atmospheres. So what is the volume of the gas? Okay. So again, this is one of those questions where you have to read it to pick out the different terms, the P1, the V1, and so on. So let me do this here. So what I would say is, based on the information provided, this here would be V1, this here would be P1, this here would be T1, and then this 20 here would be T2, and this would be P2, and the question is asking for V2, all right? So remember, the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2, all right? The question is asking for V2, which is this right here. So when we rearrange this, we're going to get V2 is equal to P1 V1 T2 divided by T1 P2. Now we need to convert the temperatures to Kelvin. So the 20 degrees here would be equal to 473 Kelvin, 473 Kelvin. And for the 20 degrees here, when you add 473 to that, I'm sorry, when you add 273 to that, that becomes 293 Kelvin, all right? So we put the numbers in. So P1 is 700.0 millimeters mercury times V1, which is 500.0 liters times T2. What's T2? 293 Kelvin. And then we divide all of that by T1, which is 473 Kelvin, times P2, which is 30.0 atmospheres. Now, you'll notice that P1 is expressed in millimeters mercury, but P2 is expressed in atmospheres. So you know what we need to do, right? What do we need to do? Anybody? What do we need to do? If we have P1 expressed in millimeters mercury and P2 expressed in atmospheres, what do we need to do at this juncture? How about you guys out there in Zoom? What do you think we need to do? No idea? Remember we said that whatever the units of P1 is, the units of P2 would have to be the same, right? So if they have different units, then what do we need to do? Convert either the value in millimeters mercury to atmospheres or vice versa. So it doesn't matter which one you do. I'm just going to choose to convert the atmospheres to millimeters mercury. And if you look up in the tables in Canvas, you'll see that 1 atmosphere, hope I can squeeze it in here, is equal to 760 millimeter mercury. All right? So the millimeter mercury units will cancel out. The atmosphere units will cancel out. The Kelvin units will cancel out. So the final units here would be in liters, whatever the value or the answer is. So let me do the calculation. So that would be 700 times 500 times 293. And then I'm going to divide that by 473 times or divided by 30 times 760. Okay, so according to my calculations, hold on, this can't be right. Let me try this again. Okay, this is more like it. So according to my calculations, the answer is 9.51. 9.51 liters. All right, and that's basically how that is done. Okay. All right, any questions about this? Any questions? Any questions? All right, so basically, if you understood what I just did, then you should be able to do the questions under the combined gas law section. All right. All right, so I leave you to do that plus the others. And I'm going to collect this assignment next week, this time, all right? So make sure you do these. Also, let me just say that I have published the videos for, let me see here, modules. I've published the videos for chapter 11. And as you can see, there are only 2 videos there. So make sure you watch those videos in preparation for next class, all right? And also, in regards to your tests, I have not picked them up yet. I plan to do so today, and I anticipate that I'll have them graded and returned to you by this weekend, all right? I'm aiming for Friday, but maybe Saturday would be the day that that will be done, all right? Okay, so that's pretty much it. I'm going to stay here for the next couple of minutes if you have any questions, because I have a class in here immediately after, so. What's up?
I was trying to like log on to the testing center.
Oh, you're the one who emailed me? Okay, did you call them?
I called them and they said they have an available seat today. I was wondering if I could take it because this is what it was saying. Like it doesn't even have the time where I can even like.
Oh, okay. You didn't allow you to schedule the actual time, right? So where are you gonna do it here?
Yeah.
Okay, yeah, I have no problem with it.
Okay. They said 12:30 and then I think it's like an hour and a half that you
Okay.
have to do it. So I'll have it done by 2 then.
No problem. No problem.
And can they hear me?
What's that?
Can they hear me?
I don't know. I can mute it.